Poster presentation entitled NOAA ACSPO version 2.8 Thermal Fronts Product, presented by Irina Gladkova on behalf of NOAA SST team consisting of Yuri, Kihai, Olafur, Jonasson, Alexander Ignatov, Veronica. NOAA produces thermal front products from various sensors on board polar orbiter and geostationary platforms in original level 2P swath projection and level 3.02 degree gridded equilateral projection. Level 3 products are of various types: uncollated, collated, and super-collated. Two fields are reported in ACSPO version 2.8, SST front position and SST gradient magnitude. The first variable is a binary indicator of SST front position. It's set to 1 where front is present and 0 elsewhere. The second variable is the SST gradient magnitude, representing a rate of change in physical Kelvin per kilometer units. In this study, we use L3S LEO daily product, which belongs to ACSPO family of multi-sensor gridded 0.02 degree resolution super-collated products. The L3S daily combines PM and AM day and night SSTs into a single daily L3S SST that is normalized to a nighttime viewing condition. Next set of slides show examples of ACSPO SST products that have frontal layers. On the left side, it's SST without cloud mask, and on the right side is SST with the front position overlaid. This particular granule is from VIIRS NPP, May 13, 2024. This is a daytime granule. All examples here are shown in the same Mercator projection for comparison purposes. This is an L2P swath projection granule. This example is also L2P SST from VIIRS NPP, but it's a nighttime granule. SST without cloud mask, and on the right side SST with thermal fronts overlaid. Again, this is same Mercator projection for comparison purposes. The third example is the L3S daily SST product. This is the type of SST we use in this study. It combines the daytime and the nighttime from various platforms, and it's normalized to the nighttime viewing condition. This slide shows two examples of level 4 analysis SST for comparison purposes only on the same day, May 13, 2024, using the same Mercator 1 km per pixel projection. On the left, it's 0.01 degree MER level 4 analysis, and on the right is 0.05 geopolar blended level 4. Level 4 products are gap-free. This makes it more convenient for a computation of gradients and detection of the thermal fronts. As this example shows, they not always have all of the features present in the original level 2P satellite-derived products or even collated level 3S. An evaluation of a thermal front product is a challenging task. The first challenge is purely mathematical, because the numerical computation of a derivative from the noisy measurements is an ill-conditioned problem. The second challenge is what should be used as a ground truth. There exists a dense network of in situ SST measurements. These are from buoys, Argo floats, drifters, and ships. Buoys are stationary, Argo floats are too sparse, and the drifters sit most of the time on one side of the front. Ships can be used for validation, but these in situ measurements are usually at the coarser spatial resolution than the satellite-derived, also noisy, and recorded at the coarser quantization level. The last challenge is complicated by the fact that ships is one-dimensional, while satellite-derived SST is two-dimensional. Therefore, the validation process cannot be by direct comparisons of values at the similar geographic locations at nearby time of acquisition. We performed an assessment of the matchups between ACSPO L3S daily product and in situ ships data in the vicinity of the thermal fronts, focusing on examples when in situ path intersects strong thermal fronts and the gradient direction matches the path of the ship. This study used in situ measurements for December 2023, available in NOAA IQUAM system. The bar plot shown here depicts the detected front counts in the logarithmic scale. As we could see, there are mostly weak fronts. This axis, the horizontal axis, is the gradient magnitude in Kelvin per kilometer. Our focus is on the strong fronts, and there are not that many of those present in the monthly global L3S gridded data. The scatter plot shows the values of the SST rate change versus the angle between the SST gradient and the ship's track. The smaller the angle, the more aligned the path with the gradient vector, and this axis is the gradient magnitude. So the highlighted rectangle contains the handful of examples when the gradient magnitude is high and the angle between the two vectors are small. This slide shows one of the examples when the ship's path was nearly orthogonal to a strong thermal front. The first figure shows the SST image, and the ship's path is indicated here by a black line. The second image shows the gradient magnitude in Kelvin per kilometer, specified only at the thermal fronts detected by our product. The third figure shows the SST values from both sources, the ships that are rendered in blue and the SST from the L3S files marked here in black. The region where the ship's track intersected the storm front is encircled here in this one-dimensional plot. As we could see, the shape and the position where the increase occurred in the ship's observations agree with the L3S data quite well, but the gradient that would be measured from the L3S data would obviously be larger than the one measured from the ship's observation, just purely because the resolution of the ship's measurement is much coarse. When estimating the rate of detection of false fronts, it is important to consider the ship's track that coincide with the gradient direction of satellite image. This is because the arbitrarily strong front oriented nearly parallel with the ship's track may not be detected in the ship's data. Here's an example of the weak front, but that's the case when the front is nearly parallel to the ship. So in this particular location, there might be no sign of presence of the front, judging from the ship's data. The second example is from Alboran Sea on December 3rd, 2023. There are several locations where ship track is nearly orthogonal to the SST fronts in this case. The largest gradient is highlighted. The same as in the first example, we show the SST image from the L3S, the gradient magnitude at the identified thermal front locations, and the SST from both sources, the ship and the L3S. Again, the ships are rendered in blue and the L3S is rendered black. We could see that there are several locations where the ship crossed the thermal fronts at the nearly orthogonal direction, but we're interested in the ones that corresponds to a larger rate of change. So that would be the case. And again, as in the previous example, although the shapes are similar and visually agree quite well, the actual measurements of rate of change would be lower for the ship's measurement than for the two-dimensional high resolution satellite observations. Detection rate of fronts reported in L3S can be assessed using ship's measurements in the following way. As we move along the ship's path from one location to the next, we can consider the line segment connecting the consecutive ship's locations where the measurements were taken and see if it crosses the thermal front identified by L3S product. So from one location to the next, we will be reporting whether it crossed the front or not. We also will be recording the distance between the consecutive ships' locations and the rate of change determined by the ships as the absolute value between the SST measurements within this line segment divided by the distance between the consecutive locations. So all of that will allow us to stratify this detected fronts into different categories. So this bar plot shows the distribution of the front detection rates by rate of change measured by the ships. So we'll consider the two extreme cases, the very first bin and the very last bin. The very last bin corresponds to all of the instances where the ship's rate of change was around 0.2 Kelvin per kilometer. In those particular cases, we always identified some sort of front within the satellite imagery. It doesn't necessarily mean that the SST's gradient magnitude was 0.2 Kelvin per kilometer. They could be of the different strengths. It only means that if we will choose as the ground truth, as a threshold for our true positive, meaning that if the ships differ, consecutive measurements, the SST differ by roughly 0.2 degrees, we will see that there is something there. So in those cases, we identify the fronts. Now, the very first bin is where there was almost no change in the consecutive ships observations. Nevertheless, there's some amount, not too many, but there's some amount of line segments were identified as they crossed some fronts. Those fronts could be very weak fronts, as we could see on these two examples. They're at the smaller values, but nevertheless, they were identified as a potential features that separating two water masses of different temperatures. So the fact that it's nearly zero rate of change in the ships could be attributed to the fact that ships' observations are quantized, so they could be rounded to the same value, while in reality they were slightly different. And everything else falls between these two categories. So if we'll take, for example, 0.15 Kelvin per kilometer as a threshold at which we will say that our ground truth is a true positive, then our detection rate is pretty high. As we start decreasing this threshold level to smaller values, then our detection rate is decreasing, which is not unexpected. So in these scenarios where we don't really have the ground truth in the regular statistical sense, where we could build the confusion matrix and say this is the amount of true positives and the amount of the true negatives, and we can compute all the statistical, predictive values that could be indicative on how well our classifier is doing, our true positive or true negative really depends on how we set the threshold. And it's not very clear at which particular level this threshold measurements should be taken. So something to be investigated further. And by the way, in all of these examples, the threshold for the distance between the ship's observations were set as the 35 kilometers. So all of the participants in here are not further apart than 35 kilometers, which is a pretty big distance to be used in the comparisons with the high resolution satellite imagery as is. So more to follow. But for now, this concludes the current status of this particular study. In the summary, NOAA produces thermal front products from all platforms processed by ACSPO system in swath and gridded projections. SST frontal product is routinely monitored by NOAA ACSPO Regional Monitor, that is our online ARM system. The first set of examples shown in these slides are taken from this online system. So it conveniently displays everything mapped in the same Mercator projection, so different products could be compared side by side because they are remapped on the same projection. Visual evaluations done up to this point suggest that derived frontal products appears reasonable and realistic. Initial analysis presented here using 1 month, December 2023, of the L3S daily and in situ ship measurements indicate good agreement given the difference in the spatial resolution and the fact that the observations are noisy and quantized. We will continue routine monitoring using NOAA ARMS online system. We also plan to use for front product validation the sail drones that NOAA has recently been deploying. These have newer technology and have potential for higher spatial resolution and in situ measurements across the SST fronts. Thank you for your attention.